Well, welcome everyone. Welcome to my session. It's on testing resiliency using chaos engineering. My name is Seth Eliot. I am the Principal Reliability Solutions Architect for Well-Architected. And if you don't know what Well-Architected is, we'll get into that in just a moment. So Werner Vogels is our CTO at Amazon, and he said, we need to build systems that embrace failure as a natural occurrence. Well, what did he mean by that? Well, failure is part of any sufficiently large and complex system, such as a data center, for instance, and hard drives and power supplies are failing in the data center all the time. So what does he mean by embrace failure? Does he mean just let things fail? No, not at all. He means we do not let failure affect our services. We find ways to mitigate it. Now, we, in this sentence, means AWS. AWS is responsible for abstracting away those hard drive and power supply failures from you so you don't even see them. And we're responsible for building these highly resilient services in the cloud like DynamoDB. But we also is a shared responsibility model. What I described about we in AWS, that's the resiliency of the cloud. We're responsible for that. But we is also you. When you build your workloads and systems, you must build them to be resilient in the cloud using AWS services and resources that we supply for you. And you have to build them to be resilient and you have to test them. And that's what this talk is about. So if you want to build resilient services, a great place to start is the AWS Well-Architected Framework. So I am the reliability lead, and reliability is one of the pillars of the framework, and the one we're going to be talking about today. But there are in total 5 pillars. So there's operational excellence, security, reliability, performance, and cost. Now, when you look at the reliability pillar of the Well-Architected Framework, it talks about certain design principles and best practices. All of our pillars cover the best practices. That's how you learn what the best practices are. So that's what Well-Architected Framework is, learning best practices. But we also give you the ability to measure. Take your workloads, your systems, what have you, and you can use the Well-Architected tool. The Well-Architected tool is available to you today in the AWS console. It'll ask you questions and ask you what best practices you're doing and not doing. And then you can improve. Based on what you've answered in the Well-Architected tool, it'll give you an improvement plan. So if we're going to be talking about resiliency and testing resiliency, it's good to define it. So the reliability pillar of Well-Architected defines resiliency as follows: the ability of a system to recover from infrastructure or service disruptions. Again, that goes back to what Werner was saying before about embracing failure. And as I said, there are design principles in the reliability pillar. There's 5 of them, but I only list 2 of them here because these are the most important ones for this talk. One is to automatically recover from failure. Now, there's a couple pieces to that. One is recover from failure. Okay, so if a failure occurs, you have to recover from it. But to do it automatically, that automation is going to help you. It's going to be faster, and it's going to avoid any errors introduced by manual processes. Now, the second design principle I want to talk to you about is testing your recovery procedures. That's super important because if you don't test those recovery procedures, if you've designed recovery procedures in your workload, but you've not tested them, you don't have recovery procedures. So that's what we're going to talk about today, which is automatically recovering from failure and testing it. So let's start with just a brief overview of how you'll use AWS to automatically recover from failure. To do that, we want to introduce you to the Well-Architected tool. As I said, we're going to show you what the Well-Architected tool looks like. And this is one of the questions from the Well-Architected tool, which is how do you use fault isolation to protect your workload? Now, using fault isolation as a way to automatically recover from failure is one of my favorite tools in the toolbox for being able to design resilient systems. And you see the best practice down there at the bottom. It says deploy the workload to multiple locations. Now, we say locations, but if you're thinking about your workload in AWS and you're thinking about what multiple locations I'm going to use, I want you to think about availability zones. Availability zones are your go-to for deploying to multiple locations. So I need to explain to you what availability zones are and how they relate to AWS regions. So AWS regions are pretty easy to understand, okay? They're basically physical locations around the world where we cluster data centers. And if you look in this map, you can see we have 24 of them. Now, in each dot on that map is a AWS region. Now, in each one of them, I'm not sure you could see it, it's a little small, is a number. So let me zoom in there. That number is the number of availability zones. So you can see the one I zoomed in on has 4 availability zones, providing 4 different locations for you to deploy your workload that are fault isolated from each other. You can also see there's 2 transit centers, and that's also providing that resiliency for the networking. But the availability zones are what you want to focus in on here. What is an availability zone? It's one or more discrete data centers. Okay, so the one or more discrete data centers in each availability zone are separated from the other availability zones. They have their own separate redundant power supplies, networking, and connectivity. And perhaps most importantly, they're separated from each other by a physical distance, a meaningful distance. What do I mean by a meaningful distance? I mean that Okay, the redundancy there is going to protect you from the component failures. EC2 failure fails in one availability zone, it's not going to affect another availability zone. But that meaningful distance protects you against disasters. If there's an ice storm or a flood that does ultimately affect one of our availability zones, it's unlikely to affect the other availability zones because they're separate. They're completely separate buildings with their own power supplies. And to show you how we design using multiple availability zones, multi-AZ, multiple availability zones, I want to show you this three-tier architecture. It's a pretty simple, straightforward architecture. It's making use of EC2, which are virtual servers, AWS EC2, that are virtual servers. And it's using three availability zones, Zone A, Zone B, Zone C. Now, if you start off at the top, the elastic load balancer is where the traffic's coming in. It's going to take traffic from the users and route it to the proper compute resource. And even though it doesn't show it on the diagram, you do configure your elastic load balancing to be in each of these availability zones. So you pick which availability zones it has a presence, and if there's a problem in one zone, you still have the other zones to still do elastic load balancing. The NAT gateways are for traffic going the other direction, out to the internet, and similarly, it's pretty obvious that they're redundantly deployed across the three availability zones. Now here we are at the compute layer. These are the EC2 instances themselves, and they're in an auto scaling group. So we have three of them here. Obviously, you can have as many as you want, but they're deployed again across the three availability zones redundantly. And then at the data layer, Amazon Relational Database Service, or RDS, you can see that I have a primary in Zone A and a standby in Zone B. That means whenever you set up a standby, it's going to be in a different availability zone than the primary, again, to give you that redundancy and be deploying to multiple locations. You can also see there's read replica there too. That gives you an additional resiliency. That means your read workloads, when you're doing reads from the database, it can be done from yet another availability zone. Now, if we look at S3, Simple Storage Service, or Amazon DynamoDB, they don't look like they're in any availability zone, but that's kind of deceiving. They're actually built automatically without you having to lift a finger to be redundant across multiple availability zones. Both the data tier of each of these services and the compute tier are redundantly deployed across multiple availability zones to give maximum resiliency. All right, so what does this look like in practice? As we said, we have to be embracing failure and designing our workloads to be as resilient as possible. So what happens when there is a failure? This EC2 instance here fails. What happens when that failure occurs? Well, the elastic load balancer is constantly running health checks on each of your EC2 instances. And they're health checks that are checking the health of your application running on that instance. So when the load balancer sees that one's unhealthy, it's going to no longer route traffic to that one. This is going to ensure availability to your users. If there's an instance that can't serve traffic, can't serve requests, we don't want to route traffic to it. We're going to route traffic to the healthy servers, and they're going to be serving requests to your users, and you maintain availability. Let's look at how auto scaling works. Now, this is a slightly different way to look at it, but it's, again, the same three EC2 instances. Now, in this case, one of those EC2 instances dies, like we showed you before. Now, your auto scaling can be configured in many ways. And one way you can configure it is say, I want to have at least 3 instances. So the auto scaling is similar to the load balancing, is running health checks. And when it detects that an instance has failed, it's going to replace it. And therefore, you'll be back at capacity. Now, the thing to keep in mind here with this particular mode of auto recovery is to look here. In the reliability pillar of the well-architected framework, question 5 says, how do you design your distributed system to withstand failure? And if you look at the best practice I circled there on the bottom, it says, make services stateless where possible. That means you want to offload state off of that server. You don't want to be keeping state on that server, because if that server dies and is brought back, then you have a seamless replacement, no loss of availability. If there were state on there, you'd lose that state and you'd have some loss of availability. And RDS, Relational Database Service. So if you look here, you got the primary in Zone A and the standby in Zone B. If the primary has a problem and dies or can't serve requests, then the standby is promoted to be primary. Now, it's not only promoted to be primary, but it takes over the DNS name that the primary originally had. So from your client's point of view, they can just continue making requests seamlessly. And again, we have that read replica there for additional resilience. Now, this is for RDS in general. For Amazon Aurora, which is the built in the cloud version of RDS that we offer, it's even better. It doesn't have the concept of a standby, but that's a good thing. What it actually has is you can have up to 15 read replicas, and you decide which read replicas are going to be promoted to primary if something happens to your primary, and that happens seamlessly. Okay, so that's a little bit of a brief overview of how to design your systems or your workloads to automatically recover from failure. Now let's talk about the meat of this presentation, which is about testing resiliency using chaos engineering. Now, let's define chaos engineering, and I think a great definition is at the Principles of Chaos Engineering site, which you could find at the link you see there. And it says, chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand the turbulent conditions of production. There's a lot to unpack there, all right? Let's talk about experimenting. If we're talking about experimenting, you might think of a scientific experiment, and that's exactly right. It's using the scientific method. And build confidence. That's super important, because some people hear about chaos engineering or chaos testing and they think it's just creating chaos and that's going to decrease my confidence. But you actually want to build confidence by doing chaos engineering because, as Werner said early on, production is turbulent. Failures happen in production. It's just a fact of life, and we want to be able to design to embrace and mitigate that. So as I said, chaos engineering is about the scientific method. So let's look what that looks like. We'll start in the upper right-hand corner of this diagram and look at steady state. Steady state means your service is running, it's offering high availability, and it's available to your users. That's steady state. So then we make a hypothesis. We formulate a hypothesis. The hypothesis is, given some event that could potentially affect steady state, potentially affect the availability of our service, we hypothesize that our service will remain unaffected. Our service will remain high availability. This is basically a null hypothesis. Then you run an experiment. That event that you put in your hypothesis, you simulate it. You simulate whatever that event is, and you actually try it out for real. And then you verify, did it affect availability? If it didn't affect availability, you're still at steady state and you're continuing around this circle. If it did affect availability, now you have an opportunity to improve. Assess what happened, understand the results, understand what you need to do to maintain availability, and then run the experiment again. That's the dotted line. And then once you do that and you're maintaining steady state, you're going around the circle again. That's how that works. So I said run an experiment by simulating an event. What kind of events am I talking about? Well, we already talked earlier about servers dying, so that's a hardware event, right? But there's also software failures like bugs or malformed responses. But I want you to think about it. There's not only events don't have to be failures. This last one here, like a spike in traffic or a scaling event. If your service is hugely successful and you have tons of users coming to it, you might see a spike in traffic. You want to be able to handle that and still offer high availability despite getting a huge spike in traffic. That's not a failure, it's a good thing, but it's a kind of thing you might simulate as part of chaos engineering. So any event capable of disrupting steady state is on the table for doing chaos engineering. So chaos engineering is not new. The name is sort of new, but the concept's not new. So when I joined Amazon back in 2005, they were doing this thing, and this is pre-AWS. This is the consumer side of Amazon, the side you buy stuff on. And they were doing something called game days. And there was a fellow named Jesse Robbins who created and was running these game days. And I mention him by name only because it was really interesting. He was also a professional firefighter. So he took his experience at disaster recovery and disaster response and applied it to these game days at Amazon. They would formulate a scenario, like for instance, a scenario that our data center in Virginia has burned down and it's offline. That's the scenario. And then we'd come up with ways to simulate that and share that with all the teams and give them an opportunity to prepare. They should already be resilient against that happening, but we tell them that this is what we're going to be simulating. And we don't tell them the exact date. We told them a range of dates, like a week or so. And we say, in this week, this is going to happen and you have to be ready for it. Then the most interesting thing about this is when that week came along and then we launched the simulation, everything happened as if it was the real thing. All the real alarms went off, all the real emails went out, everything we did was as if the real thing were happening. So it was a great simulation. And then we'd assess, did we maintain availability like we expected? And if we didn't, where do we need to improve? Now, 2010 is probably where you heard about chaos, right? This is when Netflix launched and talked about their Chaos Monkey. The Chaos Monkey was a service that they launched that would go out and randomly kill servers in their data centers, right? So randomly killed servers that their workloads were running on. So that's probably when you first heard about it. Chaos Monkey is still around today as an open source project, so you can check that out. Now, 2016 is when the Principles of Chaos were published on GitHub. That's the first commit I found. And that's where I first learned about the term chaos engineering. It probably predates that a little, but this is where the Principles of Chaos talked about applying the scientific method and all of the approaches we're talking about today. So I just said that Chaos Monkey is an open source tool. There are other open source tools out there that can do this. There's commercial tools that could do chaos testing, so why not just use these? And if you walk away from this talk and say, yeah, I'll use those, then I say the talk was a success. I got you to do chaos engineering. However, some of you might not be comfortable diving in and start using these tools right away. So I want you to be able to walk before you can run. So in this case, walking is getting you as engineers to feel comfortable with chaos engineering. And a good way to get you comfortable is by showing you how you could design your own event simulations, your own failure simulations in any language you want. Now I'm going to be showing you a demo today. And the demo is based on a hands-on lab that you can run on your own. In that hands-on lab, we have failure simulations written in Bash, Python, Java, PowerShell, and C#. But you can do whatever language you want. And we're going to not only show you can do it in the language of your choice, we're going to show you could even write a simulation that does an entire availability zone failure. So we're going to show you that and then make you more comfortable with chaos engineering. So as I said, chaos engineering is about the scientific method. It's about experiments. The experiments, we're going to do two experiments actually. We're going to do a component failure and an availability zone failure. And for our architecture for the demo, it's going to look like this. It looks really similar to the architecture I showed you earlier. I guess there's no DynamoDB, that's one difference. The thing to keep in mind is there's going to be exactly 3 EC2 instances in 3 different availability zones, and they're running a very simple web server. And that web server is grabbing an image from that S3 bucket and serving it up to you. And that web server is also going to serve up some metadata that we're going to use as part of the demo. And we have 2 hypotheses. Hypothesis 1 is if an EC2 instance dies, then availability will not be impacted. Again, this null hypothesis. And hypothesis 2 is if an entire availability zone dies, then availability will not be impacted. How can we make these hypotheses? Well, we expect, based on our design, that load will be adequately served by remaining EC2 instances. As I showed you earlier, the load balance will only send requests to healthy instances. We expect that the load balancing will detect the unhealthy instance and reroute the request. That's what I was just saying. And we also expect that auto scaling is going to replace the bad instance. Now, for hypothesis 1, where we're just killing a single EC2 instance or simulating failure of a single EC2 instance, it's going to replace it in the availability zone it originally came from. Now, hypothesis 2 is a little different. The entire availability zone is out of commission. So it can't put the new EC2 instance there. So it's going to put it into one of the other 2 remaining availability zones. All right, so now time for the demo. We're going to demonstrate component and availability zone failure as an experiment. And as I said, this is based on a hands-on lab. You can get to the lab at that link there. So feel free to run that at your leisure after this talk. Okay, so what do we see here? We have 3 EC2 instances just like it showed in the diagram. They're in zones A, B, and C, 1 in each of the availability zones. And these EC2 instances obviously have instance IDs. Every EC2 instance has an instance ID. Now let's look at this website. This website's a very simple site. It's a bit ugly, and it's serving an image from an S3 bucket. But I want you to look up here where it says availability zone. This is where I'm always going to be drawing your attention. See A, B, C. As I refresh the page, you can see it's serving requests from each of the 3 different EC2 instances in each of the 3 availability zones. So that availability zone metadata is very important. I want you to keep an eye on it whenever we're refreshing. Now we're going to run an experiment. We're going to use the Bash versions of our scripts, and we're going to do a fail instance. We're going to simulate failure of a single EC2 instance. So we're going to say fail instance, and we're going to run that command, and it's going to tell us, oh, I need a VPC ID. Not a problem. All 3 EC2 instances are in the same VPC, so we give it the VPC ID, and we run it, and you see it says terminating. I want you to focus on the last digits of the instance ID, 76F. It terminated EC2 instance 76F, and here's 76F right here in zone A. If I refresh this, we see that 76F is now shutting down. It's exactly as we expected. We were simulating a failure of that one instance. Now that instance is no longer serving traffic. It's no longer healthy. And this is exactly what we wanted to see. Right now it's in the shutting down state. Eventually it's going to go fully into the terminated state just in a few moments. Now let's check out our website. We're going to refresh it. Keep your eye on the availability zone, like I said before. B and C, B and C. It's no longer being served from A because there's not a healthy instance in A. Now that instance in A is going to be replaced, but it isn't ready yet. So no availability impact so far, hypothesis confirmed. This is the elastic load balancer. These are the targets of the elastic load balancer. You'll see it's targeting B and C. No longer targeting A because it detected A was unhealthy and removed it from the list of instances it's targeting. Here's the auto scaling group. Now you can see it still has the 3 instances in the auto scaling group, but you see the first one, the one in A, the one we terminated, is showing as terminated. Now the auto scaling group's job is to maintain 3 instances at all time. So if we go here, you can see that that instance is now terminated, but the auto scaling group's going to see that and fire up a new instance, which you can see right now here, again in zone A. It replaced the dead instance in zone A with a new instance in zone A. And that is exactly as we expected. So again, maintaining availability, replacing capacity. Let's take a brief look at the code we used. So the code's available on GitHub. When we look at fail instance, The first part here is just simply the part that asks for the VPC ID. Now the rest of it is really just two commands. It's using the AWS CLI or command line interface. The command line interface command to describe instances gets all the instances in that VPC, and then we have a little bit of JSON filtering to pick out one. We pick out one of those instances, and our second command here is to terminate instance. Okay, so we're terminating a single instance, and that is one of the instances in that VPC. In this case, it was the one in zone A. It's not always going to be the one in zone A, and it's as simple as that. So that when we refresh here, we see that one is terminated, while the other one is firing up, and it'll take about a minute to fire up. So I don't want you to have to wait with me for that minute. So let's say 1 minute later, we come back, and now you can see that the replacement instance in zone A is indeed up and running and hopefully taking traffic. Let's go check to see if on the website, check on the website and see if it's taking traffic. Keep your eye on the availability zone. We're going to refresh it, and you can see it's going to A, B, and C. So all three instances are taking traffic. Again, hypothesis confirmed. When we simulated failure of an EC2 instance, no loss of availability, and then it replaced the EC2 instance. So this is exactly what we wanted to see, and so we believe our system is built to resiliency standards that we need. Now, what's our next experiment? Our next experiment is not to take out an EC2 instance, but take out an entire availability zone. So fail AZ, and now it wants an availability zone to fail. So I'm going to just pick 2C, okay, before we were playing with A. Now we're going to fail zone C, and we'll see what happens. And we have to also give it that VPC ID. Okay, as we fail it, there's a lot more happening here. So the only thing I want you to keep your eye on is where it says ACL. It says ACL in multiple places. That's Access Control List. An Access Control List is a way that we can control traffic going in or out of a subnet. In this case, it's creating Access Control Lists to stop all traffic going in and out of the subnets in Zone C. So Zone C is cut off from the world. That's how we're simulating the failure in Zone C. So if we come here and refresh our EC2 instances, we see there's an EC2 instance in Zone C. Now, it's properly detected that Zone C is out of commission. Now, that still shows green there. I'll explain why in a minute. But you can see what it did is firing up a new instance here in Zone A. It can't put the new instance in Zone C because Zone C is out of commission, and it knows that. So we're going to ultimately end up with 2 in A and 1 in B. Now, why does it still show green for Zone C? This is interesting because this is where our simulation doesn't quite match with reality. Our simulation cut off all traffic in and out of the availability zone, which actually properly simulated the failure of our health check on the application. Our health check on the application said, I can't reach this, and I'm no good, I'm out of commission, and our systems responded appropriately. But this health check you're looking at the screen is not a health check on the application, it's a health check on the instance. And the instance is happily running inside its little isolated world, so it's technically still healthy, but our systems are reacting in the way we expect them to react. Speaking of which, let's go to the website and see how we're doing. So we're going to refresh it and look at the availability zones, and we see it's being served from Zone B and Zone A. It's being served from the 2 remaining EC2 instances, just as we expect. The new third instance in Zone A is firing up, and eventually we'll start taking traffic, but it's not yet ready. So serving traffic from A and B, availability, no impact on availability. I would say hypothesis confirmed. The new instance is starting up. We're not going to wait around to see it start up, but it will start up just like the other one did. So again, hypothesis confirmed. So I showed you the code previously for a fail instance. It's basically running the AWS CLI command line interface to do a terminate instances on one of the EC2 instances in our VPC. The fail AZ code is a little more complicated, but these are the main commands. We're creating, see EC2 create network ACL entry. So we're creating an ACL and we're associating it with the subnets in that availability zone. Look at the creation command for this ACL. It says block, it says CIDR block 000, which means every IP address. It says protocol all. It says port range all. It says, so we're blocking all traffic and we're saying action denied. That means we're blocking all traffic for both egress and the second command is ingress. So all traffic out of the AZ and into the AZ is being blocked. That's how we simulate the AZ failure. So just to recap, what did we do? We simulated failure of an EC2 instance, no loss of availability. Now, in the online lab, the hands-on lab that you can run later, we also have simulation of the RDS instance, so you can run that later. But here in the demo, we did a simulation of a failure of an entire availability zone. Again, hypothesis confirmed, no impact on availability, and we recovered. Again, it's in the hands-on lab. The link is there, and maybe more importantly, there's also, if you go to the lab, there's a link to GitHub. We'd love you to click through there. The reason is, again, we present the failure scripts, the event simulation scripts in 5 different languages. I'd like you to look through that. And you could run through, and also on GitHub, you can contribute. It's an open source project. Feel free to contribute, make it better. And if you have any problems running the lab, GitHub Issues is a great place to file any bugs or feedback. All right, so this lab that I showed you, this demo, simulated the failures using the AWS CLI, or command line interface. Now, in this hands-on lab, we also have Java and Python versions, and those are going to be using the AWS SDK. We also have PowerShell versions, which are going to be using AWS tools for PowerShell. So 3 ways you could simulate events. A 4th way you can simulate events, and that's not part of the lab, but I think is really awesome, and I have the link to it there, so if you want to check that out, is using AWS Systems Manager. Now, AWS Systems Manager, its main job is to run automation on AWS resources for you. And it's really good at running things on the EC2 command line. So you might have heard of stressng. Stressng is a Linux command line utility that can simulate CPU load and disk load. Well, you could tell SSM to run stressng on one or multiple of your EC2 instances, and you could be doing a simulation of high CPU load or high disk load. It's a really great resource. Check it out. All right, let's talk about making this real. What do I mean by making this real? Well, I want to quote from the great Robin Williams and say, reality, what a concept. When you see this quote, I want you to be thinking to yourself, what is reality for me? What is reality for my systems? What is reality for my workloads? And if you think about that, I want you to come to the conclusion that reality is actual production. Reality is actual users. Reality is my workload deployed and serving actual real users in production. And the thing to keep in mind here is that you've designed your recovery from failure and automatic recovery from failure based on certain assumptions of what failure would look like and how your system will respond to it. But you got to keep in mind, reality might differ, right? Reality might disagree with you. So we want to get as close to production as possible. So what does that look like? Well, if you're looking at traffic patterns, like what traffic am I going to use to do chaos engineering on my workload, you could do record actual user traffic and replay it. That's one way to get close to reality. Another thing you do is shadow testing. Shadow testing is where we fork or clone user traffic as it comes in live and send it to a test deployment that doesn't interact with the user. So that's another way to do it. Now, the last option there is testing in production, and that might sound scary. And I don't mean just throw it in production. I don't mean just throw it in production without any mitigations. What I mean is if you have a system that's designed to be resilient and you've reached a maturity in your chaos testing and you have events that you're confident will be handled, then testing that production is the closest you can get to production, and that's perfectly a reasonable thing to do. If you're looking at the environment you're going to set up for chaos testing, well, the nice thing about AWS and the AWS cloud is that you could set up an environment, infrastructure, and that looks appreciably like your production system. So you have a production system, you want to set up a test system for doing chaos engineering, it could look pretty much exactly the same. However, again, if you want to get closest to production as possible, testing production with the right mitigations, mitigating risk is a legitimate way to go. Finally, I want to talk about events. These events are simulations, right? By the definition, they're not the real thing. They're not real failures, they're simulations of failures. So you need to be constantly looking at production, looking at how your system operates in production, and when failures do occur, real failures, how did your system react to production? Take all this data and roll it back in and always iterate on your events and always be improving your events so your simulations are as close to production as possible. Now, I talked about game days earlier at Amazon, but I didn't really define what a game day is. Now, a game day is not just about testing your software, about testing your infrastructure. It's really about testing your systems, processes, and team responses. It's the whole thing. It's being as realistic as possible. So it starts with people, right? You get the team involved, whether it's developers, operations folks, managers, whomever needs to be there is part of the game day. And it starts off with a briefing explaining what is a game day, what's going to happen, and who are the roles, what are the roles you play during game day. Now, this planning stage is really important. This is where you pick the scenario. Like I talked about earlier, the scenario for Amazon.com in one of our game days was burning down a data center burning down in Virginia. That was the scenario. What events are we going to use to simulate that scenario? And I don't even know the specifics of it, what we did in Amazon at the time, but how are we going to simulate that? We don't want to actually burn down the data center, right? We want simulated events. And the preparation part is super important. All of the service owners are in on this planning. And their systems should already be resilient to what's going to happen. But they should still go and test locally, test in the small, so to speak, to make sure they are resilient to what's going to happen and design resiliency against this particular scenario. Then the execution happens, the actual day of, preferably in production. But again, people sometimes do game days in pre-production environments. They sometimes do tabletop exercises, whatever you're comfortable with. And in addition to capturing all the programmatic feedback from logs and such, we want people there, scribes, capturing actual feedback of what happens, what people are saying, what's happening. And the analysis is the debrief, right? We look at what happened. Did it actually meet our expectations? Did we meet our goals? And if not, what are the follow-up items to make sure we do meet our goals in the future? Ultimately, when it comes to chaos engineering, I want you running these types of tests regularly, automatically. Just like automatic recovery, I want automatic testing. A great way to do that is part of your CI/CD pipeline. Now, you can do it, again, in a staging environment, a test environment, a pre-production environment if you want. And if you reach a certain maturity level and comfort level, you can even do some of these tests in production. So in closing, I want to share this quote from the authors of the book on chaos engineering. They said, "This isn't about creating chaos. This is about making the chaos inherent in the system visible." That's important, right? It's, again, like I said before, it's not about chaos engineering. It's not about creating chaos. It shouldn't make you fearful. It actually should make you less fearful, because it should make you comfortable that you're surfacing these issues that are going to happen in production, whether you like it or not, and now you're equipped to deal with them. So what are the next steps? The next steps are A, you can do this. Again, I hopefully have lowered any fear levels, anxiety levels. And B, you should do this. Returning to the well-architected tool, the reliability pillar of the well-architected framework, question 12 is, how do you test reliability? And the best practices I've circled here are you test resiliency using chaos engineering, and you conduct game days regularly. So I hope you can do that. Here are some resources I think you might find of help. Links to the well-architected framework, links to our labs, links to our solutions library. And with that, I thank you very much. Appreciate your time. Hopefully you learned something. And please remember to complete your session survey.